More lava. On, on last week's episode, we did one of these programming challenges, and we thought we were great, but we got to the end, and there was a part 2. So this episode is part 2. Hi, Eric. How's it going?
Pray there not be a part 3.
We have no idea. There could be a part 3.
I have no idea how many gold stars we have to get through. I'm well, thank you. Well,
excellent.
Exhausted, but well, but yes. So, how about yourself?
Good. We couldn't agree on what to have for dinner, so we made 2 dinners tonight.
Oh.
And one kid went with one dinner, the other kid went with the other dinner, which in the end was successful. But we wouldn't want to do it every night.
We made some super easy chickpea curry thing. It was really yummy, very quick. Shall we jump into the
Hi, Static.
Jump into the code? Hi, Static. Whoa! Oh my goodness! So many of the peoples.
Hi, welcome.
It's okay. It's more code. We have 84 other episodes you can catch up on too. Okay. Let's
Hi, baby, welcome.
Find the button of justice.
Okay, maybe we should review part 1 for the folks who didn't.
I think if we scroll up, I get to part 1. Yeah. Okay. So we did this Advent of Code thing, which is like it's like an advent calendar except for code. An advent calendar is like a thing that you get one chocolate a day for 30 days or something like that.
Except your chocolate is a coding problem.
Yeah, except your chocolate here is a coding problem. And we did this first part, which was about lava tubes, and gave you this map. And we got stuck for a while because it turns out in this description of the problem there, very specifically, a low point is not defined as 2 adjacent things of the same number. It's only things that are uniquely of the same number. Anyways.
The numbers are like the height. It's like a height field.
Yes. And then we put in our answer, got it right, and then it's like, good job, you got a gold star. You get more chocolate coding problems.
I never had an advent calendar that gave me more than 1 piece of chocolate per day. So this is a wonderful advent calendar of code.
You really have to work for your chocolate here, or your stars, the case may be. So we haven't even read the problem. So I should do that now. So next, you need to find the largest basins so you know what area is most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, though some basins are very small. Locations of height 9 do not count as being in any basin, and all the locations will always be part of exactly 1 basin.
That's interesting. That doesn't... Well, okay, keep going.
The size, well, you have to have a winding rule in order to only be part of 1. Or maybe not winding. You have to a direction. Size of the basin is exactly the number of locations within the basin, including the low point. Example has 4 basins. Top left, size 3.
That makes sense. It's segmented off by 9s. This is also segmented off by 9s.
Yeah. Okay.
This is also segmented off by 9s.
Yeah.
And so is this one. But I think this is not the general case, right? You can have... It doesn't have to be segmented off by 9s. Like, suppose you had 2 low points that went up to like a 5 in between. Like, which one would the 5 belong to?
Or what if you had no 9s on your... Yeah. This, by the way, if you're doing technical interviews, at least last time I did technical interviews, which was a while ago, at least being on that side of the guy, this is exactly the kind of thing to do. Explore the actual problem.
Well, just interesting that the example they give you is a pretty special case where all the basins go all the way up to 9.
Yeah, this, like the first time, I was not impressed with the clarity of the problem here because we went off on what I thought was a totally reasonable direction, and I'm struggling similarly here, but I think we press on. Find the 3 largest basins and multiply their sizes together.
Okay. That is a way of getting a unique number that's likely to vary if you get it wrong.
What do you get if you multiply together the size of 3 largest basins?
Okay.
All right, so we have to write an algorithm to deal with our height field and get basins.
Can we read the invariance again? I just wanted to make sure I understood the invariance. So all locations that eventually downward flow flow downward to a single low point. Therefore, every low point has a basin. That makes sense. Like it's all of the things that flow down into it. Although some basins are very small. Okay, 9 doesn't count. And all other locations will always be part of exactly one basin. So that I think that's a really good test that we can run to make sure that our algorithm has that property.
Well, I'm trying to understand. Does it?
But I just understand how this could be. Like, should we try to construct a very simple input and try to see what the solution should be? So that so I was imagining an input that was like this. It was like 3, 2, 1. 0 is my low point.
Okay. I don't
One.
think 0 is in this, right? It's just 1 through 9.
Okay.
Yeah.
2, 3, 2, 1. Okay. And 9, 9, 9, 9, 9. I don't know how many 9s I need to make a legal input, but so my point is like there's two low points, right?
Mm-hmm.
And so I think it's clear that these all go to that low point, and these two go to this low point, but I don't know which low point to assign.
I think the way that they're demonstrating it's just a fill rule. They're just having you fill, making the 9s as edges.
So let me just put a 1 here. So what do you think the answer to this question is? Like what number would you type into the box for this input?
So what is the size of the? I'm sorry, the size of the basin is the number of locations within the basin, including the low point.
Right. So, so this one here clearly has size 1, right?
Mm-hmm.
So there's basin.
This one has size 7.
This one has size 7.
Mm-hmm.
1, 2, 3, 4, 5, 6, 7. You think all of this is one basin?
I don't see any. I mean, we can go back and look at but I don't see any way for it to not be. Eventually,
Well, like
downward.
So every low point has a basin. I think we'll agree that there are 3 low points, right?
From this previous definition of low points.
Right. I mean, we can run our algorithm from last week to see how many low points there are.
To find the low points, the locations are lower than any of the adjacent locations. Yeah. Okay. Yep. 3 low points. And it says each low point has a basin, you said?
Yes.
A basin? Every low point has a basin, but that doesn't mean a unique basin. Every low point belongs to a basin.
Oh, I see.
This is another
okay, that's
mathematical logic. I remember mathematical logic class long ago. They make you be very specific. This is the like E symbol. Yeah, well, okay. This is whatever. This is long dead brain cells.
But okay, maybe let's talk about it. A basin is all locations that eventually flow downward to a single low point.
Locations? A basin is all locations that eventually flow downward to a single low point. But what is flow is not defined?
Flow is not defined. So that's a good point. I think this is not a very well worded question. Like if I were in a job interview and I got this question, I would be asking a lot of questions about like what does it mean to flow, or like
yeah, I mean,
when you say a basin, is that a unique basin?
Yeah, but yeah, as I said earlier, I mean, you should do that in a job anyway. Like, but okay, I agree. It's not a great specifier, but I think your initial instinct that we should just try extrapolating from this example.
But the example is all a special case because each of these basins goes up against.
No, what I'm saying is that if you have no 9s, you only have one basin. I think that is the way this is just written.
Okay.
That 9s are the only way to divide a basin.
Okay. Okay. Do you want to talk about? I'm still not totally sure what we're trying to compute, but maybe we should try thinking about how we're trying to compute it.
So I see this as a coloring problem, right? So you
Mhm.
walk through a copy of the map,
Mhm.
giving numbers to your basins, right?
Yeah.
And
So
so the
like
first,
you would start by coloring each low point a different color, and
I,
then look.
I would with this, I would ignore the low points.
Okay.
This is
Well,
as I currently read the problem. Sorry, go ahead.
so keep going. What
I would just walk from the very first thing. If it is not a 9, it gets a color. And then that color floods to everything it can get to. And then you just keep walking to the next thing that doesn't have a color and
Mhm.
give it a color and flood.
Mhm. So let's say, just to give this example, you start in the upper left corner. You would, let's say, pick blue for the 2 in the upper left corner. Then it would flow downward to the 1, and then it would stop.
You actually don't even need, you can do it in a single walk. You don't need to, um, you don't need to flow any of them. You just, in your first walk, you look at your first thing. You see, very similar to our previous thing, you see it if there's anything that already has a color. That means that it is in this same basin,
Mhm.
and you only actually need to look up and left because that's the direction you're walking. If you're walking from the upper left-hand corner through, right?
Mhm.
If it has a color, you take that color. Otherwise, you assign a new color, and you go to the next one.
Okay. Should we try that?
Yeah, and we'll see. I mean, that should get the right answer for this example, and then we'll
Okay.
learn when it gets the wrong example for the other thing what they actually mean.
Okay. That sounds like a reasonable place to start. That's
Uh,
our challenge input, I guess. It's large and in charge.
yeah, that was our last week's challenge input. Okay, so can I remove this?
Can we keep it commented out? That would just be. I think it might be an interesting test case for later as well.
Great. Okay. So I see. So we can take any one of these, and we're making a new class since we got on the class train.
I feel like this thing has some useful methods in it. Why don't we just keep extending it?
I see. So we're gonna do. All right. So I have to write comments because that's just how I roll.
Mhm.
So this thing is def problem 1, something like that. Right. So that was last week,
Okay.
and so this is now going to be def problem 2.
Mhm.
Pass. I'm remembering my Python slowly. And then problem 2. Yes, I could put this in a knit block, whatever. Okay, and so we're gonna start at 0, 0, walk through at each, check up, left, neighbors in color map. In fact, you could even modify the original input, but
Oh, let's have let's try not to be destructive. I think we want to.
if as color, take that color, else take next color. Okay, so next color equals 0, whatever.
Okay, so I'm just going to move this up here. I'm going to put this like here. All the same structure we had before.
Okay.
So it sounds like we need to add some more state to our class, which is the colors, right?
We just need to make a copy of the map, and that becomes the color map.
Okay.
We could use negatives, for the colors, or there's all sorts of ways we could do it.
So colors equals. Isn't there just a way of making a big array in Python?
Isn't there just a way to like deep copy in Python? I know there's a free function called copy, isn't there? So assuming you're going to need a copy of the puzzle, so we could just do like colors is equal to puzzle, like copy puzzle. It's clearly wrong because it's not there, but you're gonna figure that part out. Well, we would typically shard when you and I used to hack together. Maybe in this I should follow you around so everyone can see.
Oh, I am not typing anything. I'm just looking at the easiest way to make an array.
Okay.
It looks like this is the easiest way to make an array. So you want me to fill it with
All right, so what's this lookup? Oh, I see. Because lookup could be okay. Yeah. All neighbors are greater than. This is just like color 4. Let's see, we kind of want this like next color. Our thing doesn't modify itself, does it? Right? Submarine map is immutable.
Yes. We could modify it. We can modify it.
Well, so I have 2 pieces of state, right? I have to record the color somewhere, and I have to have a what is the next color. So I don't know where to store those.
Okay.
Okay, so this is false.
Oh, you want to put the colors there? Okay, that makes sense.
I don't care where I put them. I just was.
That's fine. I think that's nice actually, because then we don't destroy the puzzle. We just keep it in a local variable.
So one weird thing. I see. So okay, so that would just be colors then y x and then oops. So that color 4 is just a simple check. This is like check x minus 1, y check y minus 1 x. Just the 2 things to check.
Okay. And you want to look up their colors basically, or look up their values.
Yeah, it's like if they have a color, we want to take their color. Otherwise, we want to get a new color.
We have to use the value in some way, right?
The value just checks whether this thing gets a color at all. So that's a good question. We didn't do this. This is the if value not equal to 9, or if value equal to 9, set color equals none, or whatever our sentinel value for that is.
Okay, we could use none.
Else, is none a Python thing?
Yeah, none's legit. Okay, so we can do that, right? We have the code for that. Set color is just saying, we can just continue actually, because the default is none.
Okay.
Right? This is just going to find all the 9s and partition the map.
Correct.
By 9s. Okay.
That's what I think they're asking us to do, because triggering based on low points makes no sense because they haven't defined flow, and they made a statement that doesn't make sense if you have multiple low points that each. So I think we have to fail their value first.
Okay, that's fine. So this is good. Right. So check up left neighbors. Okay, so we need to get the.
So either we can just say like here, or we do 2 lookups. Oh, we could just do.
We want to look up in the color array, right?
Oh yeah. Yes, that's a little more sensitive.
Y minus 1. We have these bounds problems here.
Yeah, you have bounds problems. That's why you kind of want like an array thing that handles this for you.
Well, we can just inflate the array. Is that what you want?
Oh,
But
sure.
why don't we make a color map class, right? Color map.
What I'm saying is you have a more general, because the puzzle has this exact problem where you just want to have a specific behavior when your X and Y are out of bounds. You want to have like a default return. But yeah, we could make a color map. And then maybe this is just our out class, like thing that's recording what we do. And then it could also have the next color, or maybe not. But yeah, you're doing the same code as the other, which is fine. In fact, we have that exact color in lookup. We could just like copy lookup.
You want to try to shortcode, or do we just want to copy it?
It's an AppNet code. Let's just copy it.
Okay.
Yeah, so I copied it. So
Right.
none, right? And this is self colors. And this does not need yet. Not exactly the identical, but it's close. Okay.
So then here we want to say colors equals color map puzzle.width.
Why are we checking against 9? Oh, I see. We're checking against max.
Then this is colors dot lookup.
Yes. And then you can write XY, which is just much easier for humans to read.
Next one. Left color. And then you'd say color equals up color or left color. If not color. Oops. Oh.
We're sort of taking advantage of the Boolean logic that none is falsy. And also that this or statement will return the latter rather than returning true.
This is sort of the way
taking
Python.
advantage. But like somebody who doesn't know Python reading this is like, like as in many typed languages, the or statement would convert this to a Boolean.
Sure.
Python does not. Python returns you the second.
This is the Pythonic way, is to abuse all these things.
Rust would not allow it.
We want to say colors dot set x y. This. Indent this.
I could just be set.
Oh, it's set.
Oh,
I never know like what's a keyword.
I hear you. We can call it set color. It's fine. Okay, and then who's holding on to next color?
So I think at this point we just print out the color map that we got.
Hold on. Oh, I see. You already did the next color plus equal 1. Great. Okay.
Right. So I just want to like print colors dot colors.
I think you're going to need a loop to make it reasonable. Oh, we'll see. All right, let's try it. Stir has no absolute width. Oh, did we make it up?
I agree.
Oh, I see. We actually did specify it as a stir.
Oh, so we just need to make the puzzle. Submarine puzzle. Or.
Oh, I see. Yes. All right. That looks reasonable. int object is not iterable.
Oh,
None
this is
or I
we
intermittent.
have range. All right, insert more ranges.
What? Whoa.
Right, I'm wrong.
Okay. Huh? Makes sense.
Okay. I may need a prettier printer to see what the heck we're doing.
Yeah, I figured we might, but if we're just eyeballing this, what is this?
Okay, so that makes sense. There's three
Yeah.
nines, which get three nuns. Oops.
Yeah.
And then all this stuff flows together. That looks legit. This one.
Yep.
Okay. Then there's a 9. Okay. I mean, it looks legit.
The 4 next to the 3 doesn't make sense.
Which
You
one?
should never.
Oh.
What happened there?
Oh, it assigned a color, and then it moved over and saw that its up color was set, and so it got excited.
Oh.
Yeah.
So my
this algorithm is not quite right.
Fast algorithm doesn't actually work.
Mm-hmm.
We have to do a flow. Okay, that's fine. It's easy. It just becomes n squared instead of O of n, right? Or worse than that, it's what is it, n factorial or whatever? Because worst case scenario, you are. I guess you could still have this logic. It's just before you need a third step, which is okay. Before we get a new, this part then just becomes an optimization. This is like the common case.
Okay.
But before we go do this, we go. No.
Mm-mm.
No.
It's the case where it's the and case, right? When there's both an up color and a left color, we need to do something different.
I think we take a totally different approach. We just go to each square, and if we go to each square, and if it does not already have a color and it isn't a 9, we fill from that square. So we do a dynamic programming approach.
Okay.
And we stop. We will never encounter a blank. It's an error to be trying to fill and to encounter another color. We will only ever stop at 9s.
So I have a different proposal for you.
Please.
So what we kind of want to do is whenever you find two adjacent things, you kind of want to union them. So I think it's like you may want to like a union find kind of data structure here.
I mean, you could always take the lesser value. Is it only this case where you have to grab a unique color, but then you find...
Like imagine we just remembered that 4 and 3 were the same color. And then we did a second pass over the colors to like in each group replace the number there with the least.
Sure. And so that's only if you check both left and up and there and. Okay.
Correct.
Yeah, sure. Let's do that. So that's a list of tuples of like color unions, basically.
Yes, I'm just trying to find if
well, you don't even have to simplify it. You can like do that in later, right? You just do color unions.
Okay.
Right? And then it says if up color and left color. Oh, why did
I don't know why we wrote that. That happened to me too.
Yeah, I remember seeing it do the exact same thing. So then we just do color. Color unions could be a set.
Mm-hmm.
Right? Doesn't Python just have sets, right?
I think I just want to map, like a map from numbers to numbers, and then you always do the least one pointing, or the greatest one pointing to the least one, and then you can chase it.
Sure. Well, you could also make them both point.
Oh, I see. Yeah, you need a.
Although, so this what I'm proposing should work. Tuple up. Oh. All right, that's the total drought of sleep typing here. Color. I'm not. This is not the most efficient way because you will end up pathologically with a very long color unions. It's probably bounded by some.
That's fine. And so then you need to do the fix up, right? So how does the fix up go?
You then walk your. Oh, this is. You're right. This would be better if you did less and more.
Yes, you just want to say min, right? Min and max.
Okay.
This is the like min of up color.
We should just save that. That's more.
Really, if it could be different, right? If up color bang equals left color and color bang equals none and left color bang equals none.
Well, what I said before should work, shouldn't it?
Without this check, you mean?
Yeah.
Okay.
Oh, I see. They could both be the same color.
Right. So then you want to make a tuple that's like less and more, right?
Yeah, or I think your map thing was fine too. Again, sorry, my brain is not running on very much sleep.
Yeah, we're just building a map. So why don't we just use map?
Okay.
So why don't we make sure that now you got to check whether.
What happens when you end up mapping again? That's the. Yeah, so this you don't have to check again. You just would have to. I guess you're gonna have to build the map again. You have to build the map again.
So this has all the data, right? So now let's see. Now we need to go fix up our color map. Right? How do we use this color union information to fix up our map?
So you could walk it and build a map like you were suggesting.
Yeah, I think we should build a map like this. So I think it's easier if we do it here, right? So we have our map. Less is more. So what we want to do is now we want to add an edge. Add an edge from more to less. Okay. And the way we're going to do that is we're going to say if the color unions more, this is like existing.
Less, or it's more, right? Always more to less, because that's what you're gonna.
This is like we're gonna need better names for these things. But if there's one there already, you have to keep getting smaller. Okay. This entry is only allowed to shrink.
This feels like this color unions thing wants to be a class.
Okay, so let's make it a class. That's a great idea.
Just because you want to like possibly have looping logic, and you want to just shove this in a.
Yep.
Because your intent is very simple.
Okay, so let's do the init.
I'm gonna make this. There's totally going to be a third star.
It's only a third star, and I don't even know. Okay, so this is like
yet another example of why interview problems. I haven't been on again the other side of interview, but like sending home interview problems just seems like a terrible idea. Because I would spend forever on them, mapping lava tubes.
This is just union find. We could just call it union find. So there's going to be union. It's going to be one of the operations. And the other operation is going to be find.
And if find doesn't, it just returns itself.
It's going to be self.aliases a or a. That's the find operation that we want to get to. The union operation is from a keyword.
Looks like it might be.
Key is going to be the max of these two.
Okay.
And
And
B.
B.
Okay. The value is going to start out being the min of A and B. And then we're going to say if current will be self dot aliases at key. If current, then self dot aliases key is the min of either the current value proposed value. If there's a current value, oops, it's the min of the current value and the proposed value.
Okay.
Let me think if that's right.
But this doesn't. This needs to recurse. So this is.
Yeah.
This is like while.
You're totally right. It needs to keep going.
So we have to do tail recursion. Either we have to call something, or we have to do tail recursion here.
And which is the case that we need to do that? Like if
It's if you're about whenever you go to set something, you need to check if it already points to something, and if so, you need to update both of them. No, not both of them. Oh man, my brain.
Yeah, union find is a fun data structure, but we got most of the way there.
Okay.
So this case, I think, is correct. If we don't have a
while current value. So this is so if we just do recursion, you would call some sort of like def inner set. And what's this?
This is the inner set, right?
Oh, yeah, it's basically replacing and returning you the value that it replaced. Oh, it's replacing you with a minimum.
I think it's just this.
Sorry. Well, we don't recurse here. Or are you keeping my while here?
Oh, you're right. This is not quite right.
Okay, I gotta shake it off. Shake it off and concentrate. Find it in here.
So should we write down the invariant, right? What is the invariant that we're trying to maintain? The invariant we're trying to maintain is that each
thing points to a smaller. You can never point
each
to
entry in aliases points to the smallest representative
of the group
of the set, right?
Oh. Well, so then why is this?
That's what this find function implies, right? This find function says if you want the smallest representative, so we can rename find to smallest representative.
Mm-hmm.
Right? This implies that the entry in the map always has to be the smallest representative for the set.
Okay.
So
you can
if
fill the map initially. That's what this is effectively doing. It's like
right. This is saying it's effectively everything is its own. When you haven't made any unions, everything is its own smallest representative, which makes sense. So let's get the smallest representative for A.
Yeah. So now you can use this in your
A equals self.find A. Smallest for B equals Okay, representative for B. So then the overall smallest representative equals the min of smallest for A okay. So I think we can't maintain this. This invariant is too expensive to maintain. So each entry that points to a smaller representative
correct
for the set. So then this smallest representative is incorrect. We should just say, so this is where we should put the loop. We should say representative equals this. I would say while there's a representative, keep shrinking it. Okay. I'm going to rename aliases to smaller.
I like that. It's a good name.
Okay. Union find is a great data structure. It's one of my favorites.
So also, like hitting this, if I was actually doing this for a coding challenge, or like if we really needed, I wouldn't chase this down. I would just do something more expensive, more computationally expensive, but simpler to code.
Mm-hmm. Yeah, but I'm just enjoying coding union find. Sure. Like I'm sort of off the lava tubes problem and onto the union find problem.
Okay.
Okay. So do we believe that this is a correct implementation of smallest representative?
Just this one. So give it a value.
I think this is do while, right? Does Python have do while?
No.
Okay.
This, because whenever you recurse, you're going to end up in the just return value case, because you will eventually hit none.
Oh, okay.
This needs to be smaller or representative. Yeah, so this is while
I think it's just easier to write this as a forever loop, right? Like while true. While true.
Mm-hmm. Yeah.
Find a representative. Representative equals none. Okay. Representative equals value. Okay.
Okay. Yep.
We're going to start with the candidate equals value.
Yep.
We're going to attempt to shrink the candidate. Okay. If
you don't want to
next.
Yeah.
Next candidate.
There you go. Because you want to say
next candidate. If not next candidate.
Yeah.
Then return the current candidate.
Yeah. Yep, that's totally fine. You could imagine that your smaller data structure might want to be able to point to itself. So it's like, this is like if next candidate is, if not, or it's equal. If it's greater, you blow up.
Or
Right?
you
In
should
our
get
current
smaller.
implementation, that's not going to ever be hit.
I think we should not do that. I don't think we should put explicit self entries in.
Okay.
Okay. So now we have smallest representative for A, smallest representative for B. Well, now that's a lot less stressful, right? We just need to add an edge from smaller to larger. Right?
Okay, so you're doing smallest.
Right, so then I think this gets much, much simplified. I think we just need less and more. I'm not going to delete all this right now, but I'm going to write what I think I need.
Okay.
Smaller is min AB.
Mm-hmm.
Larger is max AB.
Yeah.
And what I need to do is self.
Oh.
Smaller is, this is the whole trick of union find, I believe. Larger points to smaller.
But what if larger already pointed to something else? Have we lost that link?
Right, so we can't lose that link.
This is the recursion part.
Right. Okay, yeah, you're right.
So we have to do basically the same as this thing here. It's very similar, except editing, right? So it's like this is a like def record smaller, self larger, smaller. And get mad at me. It's just okay. And so candidate equals larger, while true. Next candidate. Yeah. If not, then we're done. Otherwise, we're I'm screwing it up here.
Can you verbalize what you're thinking?
But it just should be very similar. I'm having trouble thinking is the problem. If self smaller.
Yeah, so I think that the thing that like this is correct for here, right? We're done, right? So now we have to think of the inductive case.
Okay. It should be this one, right? Next candidate, and it's not smaller. It should be previous candidate, right?
Oh, you know what? No. I think I see how to do this. Could we back out of this? I think we were on the right track before. Smallest for A and smallest for B, right? So if concepts have diverged. Replit blew my mind. Okay, so if these are the same, then we're done, right? Then these things are already part of the same group.
Okay.
Return. Otherwise, then we set. Now we need this larger, smaller. Now we know that we have empty. The smallest representative must have an empty entry in the map.
Mm-hmm.
So we know what slot to write in the map.
Oh, I see. You're walking from
Right, now we get to okay. Larger, smaller. And now we get to do the fun thing that makes union find super fast. We'll do it in a second.
Okay.
Now we need to do this this thing. Larger, smaller.
But don't you have the same problem? You didn't recurse?
I don't need to recurse because I know, like, I can assert here that this is none. Otherwise, it couldn't have been the smallest representative.
I see. So what you're saying here is that you're saying you only need to chase down the small. You only need to chase down on the small side, and you set the new thing.
You chase them both down, right? You find the like smallest representative for each set, which necessarily don't know about each other, and then you teach one about the other.
Oh, but you're not teaching the smallest.
The smallest already knows about the smallest.
I know I keep saying this, but I really, it's very difficult for me to reason about this at this hour of night. I think that, I don't think the code is written as correct.
Do you want to, let's write some test cases. You want to try to think of a test case that it gets wrong?
The test case is where smaller, more, I see, smaller, more already never can point to anything. Okay. I see. Well, so
Okay.
in this, what if you've already determined? Say this thing, you have none, none, 0. Your map. So you've already determined that the third, which we call index 2, is the same as this one.
Okay.
And now you need to update it.
Well, let's write that as a test case, right? That's this, right? So if I do union find and I say union 0 and 1,
you do UF dot union.
If you scroll down a little bit, I already wrote a test case. Yep.
Okay. And then, yeah, great. Okay. So 0, 2.
Okay.
And then you want to do 1, 2.
Okay. And then you want to find something.
And then you want to find, and if we're not careful, we're going to end up orphaning. Yeah, well, then you should just find any of them, and they should all be the same.
Okay, so let's try it. So print find 0.
Mm-hmm.
And we're going to print.
Yeah, this is good to start with the test cases. Yep, 1 and 2, and they should all be 0.
And I'm going to comment out those other things so we don't run our problem. Okay, so try running it.
Poetry, more poetry.
Install the poetry.
Map. Oh, I see. It's not the map we think it is.
You see that.
It's a function map. Key error 0.
Oh, I think you need get maybe.
Get, yeah. Mm-hmm. And get takes a second candidate, which is the default, and by default it's none, and so get, yeah, yes, will return none. Yep, correct. Assertion error.
Which line? Line. Oh. Okay. So what? That's on line 245. Okay, so you broke it. Good work. What? So let's print.
Well, the reason, I mean, I can see in my head why it breaks. I don't. We have to recurse because you have to update your map. You have to have space. If you just jump over 1 initially, you have to like somehow fix them to like point in order to maintain our invariant.
Good try running this again. 2 goes to 0. So 1, 2, 1, 2. Okay. So the smallest, why isn't the smallest for 2 equal to 0? Like B, smallest for B I would expect to be 0.
Well, that's a good find.
Right, because 2 points to 0. So I would expect so I'll just print out each candidate as we go through here. Or I wish we had an actual debugger, but
We don't have a debugger?
we might. We try to figure out if we have a debugger.
Debugger!
Okay. Let's set a breakpoint.
It's debugger beta. Okay.
Right.
We have a breakpoint at line 11.
All right, we don't think we need that one.
Oh, I see.
Okay. I think we might have misclicked created a break.
All right, where are you trying to set a breakpoint? You can do it too, can't you?
I'm not sure it'll show up on your screen, so I'm not sure the audience will be able to see.
I bet it will.
You want to try?
Yeah.
I was going to put a breakpoint right. Yeah, it doesn't show up on your screen.
Bam!
Oh, it does.
It does.
Legit.
It's Replit. This is their whole shtick.
So everyone who shares a Replit has to debug together. Like I can't debug one problem while you debug another. That's wild. Okay. How do I? Oh, run the debugger.
That is a fascinating question. What things do you want to share, and which things don't you want to share, and when do you want to like go apart and come back together? And
yeah. Okay. Next breakpoint. Whammo. Okay. So where am I on the call stack? I'm here. I'm still on the first call, right? Yeah. I want to get to the second call. Okay. So now we're on the second call. We're finding for A. What is A? Oh, value is 1. That's not the case I'm interested in. I'm interested in the case where the value is 2. Okay, value for 2. This is the case I'm interested in. So the candidate is 2. I look it up. My next candidate is... Oh. You know what the problem is?
sure.
I can't edit while we're debugging. We very nicely compute this next candidate, but we never set candidate to be next candidate.
Okay.
All right, that didn't help. But okay, let's keep going. Let's debug it again.
Okay, this time with feeling.
Okay, this is still the first one. I don't want that one. Okay, this one. So now I'm on the second line of my test case. My candidate is 1. Okay. The next candidate is 0, which is what I want. What? If not next candidate.
Oh, is 0
0 falsy? Ah, Python. Got me.
equal to none? Yeah.
Python. There you go.
You fixed it?
I mean, it passed this test case.
I believe you. All right,
okay,
so
can I do my favorite thing about Union Find?
Sure.
So here's the whole trick to make
data structure I'd never heard of before tonight.
What's that?
This is a data structure I'd never heard of before tonight.
Oh, Union Find? This is a classic. So here's the trick to making Union Find fast. In the find step, you want to update the data structure.
Okay. Makes sense.
So you have a visited. I think you can, let's see if there's a way to do it backwards. I think you normally do this by recursion, and then when you unwind the recursion, you set things up. But
okay.
So let me try to rewrite this recursively. Oh, I don't want to do that.
You should know that we're at our typical hour. So.
Okay, I'm just going to put visited equals thing visited equals candidate. Well, let's not do this. It'll take a little more time. But basically, what you do is all the things you visit and you update them so that the representative that they point to is actually the smallest representative that you found.
Mhm.
And that means that over time, your map, everything ends up pointing to the smallest representative, and each of the find steps ends up taking order 1.
I see. Because that makes sense. You're it's dynamic programming again. It's right as you might as well cache the. You're like memoizing the result. It's like, well, I went and looked this one up. Might as well store it because our invariant.
Our invariant is that you found a candidate, and as you look things up, you find better candidates. You might as well remember that. And it turns out that then you can prove this amazing, algorithmic performance bound on this algorithm, and it's like some crazy function called log star that is like the number of logs you have to you have to apply or something. Anyway, it's a beautiful data structure.
I can believe that. So we didn't solve our problem, right? 'Cause we would've-
Oh, do you want to try to solve it? Like, I think we're basically there. So here we had our color unions. We'll just make this a union find. A union find.
Mhm.
And then color unions here. We just need to say, we just skip all this and just say,
Yep.
Union color and down color.
Left color. Yeah.
Okay. And then here at the end, we walk through the array again, and we just say,
Yep. Colors. Yep.
If
YX.
current.
We just. Oh, I see.
Color equals colors dot lookup y.
Mhm.
If color is none, continue.
We're gonna have trouble here with the color being 0, right?
Yeah, we'll have to fix all. Let's fix all those. You just say set color, color unions.
We also just change our next. Oh, we never used the one color, or we never used color 0. But that's
Anyway,
fine.
So then we update this. So should we just try our? I don't think we should go much farther. I think we just run our problem 2 and see if we get the. Well, that was great. Aside from that, it was wonderful.
What did I do? Was it? Hold on. This was else not color, right? Hold on. So this is color equals none. Set color, positional arguments.
Oh, okay. Just X and Y, I guess.
Okay.
Anyway, so let's solve the problem. So in row, I forget what row it was. There was some row where we had 2s and 3s next to each other.
And then basically all you're trying to do is count the number of things in each basin? Is that the... Oh, I see.
Yeah.
It's the basin size.
Yeah, I don't think we should try to solve the rest of the problem, but like the point is we solved the bug that we had encountered using the union find data structure.
Okay.
Honestly, I had more fun writing union find than I had solving this sort of somewhat ill-specified lava basin problem.
All right, well, I'm going to go throw this head against a pillow.
That sounds like a great idea. I want to do that too.
And I will see you with more brain cells next week. How can I even turn this off?
See you next week, everybody. Thanks for coming.
It was good to see you. Take care.